Hi, in this video I'm going to take you through how to answer an AQA Physics P1 paper. I'm going to go through the June 2014 paper, but I'm going to hopefully offer you some tips for addressing any paper. So, starting with question 1. Electricity can be generated using various energy sources. So we're reading the question stem because that tells us what we're expecting in the rest of this question. Give one advantage and one disadvantage of using nuclear power stations rather than gas-fired power stations to generate electricity. So we've got what we're comparing here. So it's not just nuclear over any other type, it's compared specifically with gas power. And we know that one of the problems with gas power is that it produces carbon dioxide. We also know that nuclear power doesn't do that, so the advantage doesn't produce CO2. Of course, carbon dioxide being a problem because it contributes to climate change. Disadvantage of using nuclear power is what it does produce, which is radioactive waste. Okay, 1b, we've got a calculation. A single wind turbine has a maximum power output of 2000 watts. The wind turbine operated continuously at maximum power for 6 hours. So as our two key values. Calculate the energy output in kilowatt hours. Okay, so we've got a power in watts. We need our answer in kilowatt hours, so we need to convert that into kilowatts. We do that by dividing by 1000, so that gives us 2000 kilowatts. Okay, use the correct equation from the physics equation sheet. That gives us energy equals power times time. So 2000 times 6, which is 12,000. Let me just put that in the answer box. Be careful when you're writing things with multiple zeros to make sure that you've got exactly the right number of zeros at the end, because I know that even though people have got the correct answer in the past, where they've not correctly put their answer in the answer box with the right number of zeros, they've lost the mark. Okay, why on average do wind turbines operate at maximum power output for only 30% of the time? It's not always windy. The wind speed isn't continuous, so it's not giving maximum power all the time. So not always windy. An onshore wind farm is made up of many individual wind turbines. They're connected to the national grid using underground power cables. Give one advantage of using underground power cables rather than overhead power cables. So there are a variety of answers you could give here. You could talk about the fact that they're less attractive to look at. You could talk about the fact that they are more likely to be accidentally touched and give someone an electric shock. What I'm going to go with is the fact that they're more likely to be damaged by the weather, because that's the one I feel is most likely to give me a chance of the mark being in the mark scheme. More likely to, less likely to be damaged . Okay, question 2, we've got a 6-marker question. With the 6 markers, they often give you quite a lot of information to help you answer it. So we've got information about the properties of solids and gases. Solids have a fixed shape and difficult to compress. Gases will spread and fill the entire container and are easy to compress. We have to use our knowledge of kinetic theory, so that means we're talking about what's happening to particles and the motion of particles. To explain the information in the box, you should consider the spacing between the particles, the movement of individual particles, and the forces between the particles. So we know that in solids, the particles are close together. Try not to go out of the box. In solids, the particles are close together, but in gases, they are far apart. Okay, so we've described this, but we've not yet related it to the information in the box. And what this relates to is their compression. This is why Gases can be compressed but solids can't. Okay, so we've done that one. Okay, so the movement of individual particles and the forces between the particles. Both of these two things together explain the difference between solids having a fixed shape and gases spreading to fill the container. So I'm going to talk about both of these before I relate it to the text in the box. So, in gases, particles move randomly at high speeds, but in solids they vibrate around a fixed point. So that's the movement of the individual particles. The forces between the particles. Solids have strong forces between particles, while gases have very weak forces. These things, so I'm relating it back to what's in the box, mean that solids have a fixed shape, while gases spread. Okay, so I don't need to go on and say any more than that. I've addressed all of those key points that it said that I should consider, and I've explained them and linked them to the things in the box. I haven't needed to go into the extra space at all. The extra space is really only there for if you've got really big handwriting. Okay, moving on to question 3. We've got biscuit manufacturers. I love questions about biscuits. So, figure 1 shows the way that biscuit manufacturers cook large quantities of biscuits. The uncooked biscuits are placed on a moving metal grid. They go between 2 heating elements inside an electrical oven, and out come the cooked biscuits. They turn brown as they cook. The oven has 2 control knobs as shown in figure 2, the power and the speed of the grid. So first of all is a knowledge question. Which type of electromagnetic radiation makes the biscuits turn brown? So I go back to my 7 parts of the electromagnetic spectrum: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. Which one is associated with heating things? It's infrared. Okay, suggest 2 ways of cooking the biscuits in the oven to make them turn browner. We've been shown that there are 2 dials on this oven. So first of all, power. How are we going to make them turn browner? We're going to increase the power. Our other dial, the speed of the metal grid. So if we want them to be in with the heating elements for longer, we need our grid to be going slower. And that's all you need to say for those 2 marks. It's just asking us to suggest, not to explain. Now this is an explain question. It tells us that the inside and outside surfaces of the oven are light coloured and shiny. So we see light covered and shiny, we should be thinking of those properties to do with radiation, whether things are reflected, emitted or absorbed. So let's start with looking inside the oven. The heat source is inside the oven, and we know that the light and shiny surface on the inside is going to reflect those rays. So inside, light shiny surfaces are good reflectors, so the heat will reflect onto the biscuits. Okay, but that's only answered half the question because it said the inside and the outside. So outside. Okay, our heat source is inside the oven. So we're not looking at it reflecting. It's whether it's absorbing or emitting. Well, we've not got another heat source outside. So it's not about whether it's absorbing. So it's just about emitting. Are light coloured and shiny surfaces going to emit well? No, they're not. So light shiny surfaces are poor or bad emitters of radiation. And what's good about that? This reduces heat loss. Okay, so that's the end of question 3. We're on to question 4. A note was played on an electric keyboard. The frequency of the note was 440 Hertz. What does a frequency of 440 Hertz mean? So this is effectively asking you what's the definition of frequency, and that's the number of waves per second. But it's being very specific and saying what's the frequency of 440 Hertz mean. So that means there's 440 waves per second. Okay, the sound waves produced by the keyboard travel at a speed of 340 meters per second. Calculate the wavelength of the note. Use the correct equation from the physics equation sheet. Give your answer to 3 significant figures. Right, we need to get to an answer before we worry about that last bit. So, correct equation from the physics equation sheet is wave speed is equal to frequency times wavelength. So we're going to have to rearrange that. To do that, we need to divide both sides by frequency. So wavelength is equal to speed divided by frequency. So our wave speed was 340 and our wavelength, looking back, was 440. If I put that into my calculator, 340 divided by 440 gives me 0.77272272 and so on. Okay, we need this to 3 significant figures. So we're looking at 1, 2, 3. Our next figure beyond that rounds up. So we're going to get 0.773. If you don't round that up right, you can only get 2 out of the 3 marks. Okay, figure 3 shows a microphone connected to a cathode ray oscilloscope being used to detect the note played by the keyboard. Here we've got figure 4 showing the trace produced by the sound wave on the CRO, and then a second wave was played with a different wavelength, and that's shown in figure 5. The settings on the CRO were unchanged, which is useful because that enables us to make a comparison. What 2 conclusions could be made about the second sound wave compared with the first sound wave? So, first and most obvious thing, this wave is taller, the wave in figure 5 is taller than the one in figure 4, which tells us that it is louder. Okay, and the scientific word for that height of that wave, we're going to give us the reason, is it has a bigger amplitude. Okay, the next thing we want to look for is the number of waves we've got. So we've got 2.5 complete waves there. We've got 4 complete waves there. So the wavelength is longer in figure 4. which means the frequency is higher in figure 5. So frequency is higher means it's higher pitched. And I'm going to say that's because it has a shorter wavelength. The waves closer together in that image. And then we do a complete change of topic onto question 5 and find out about Iceland generating nearly all of its electricity from renewable sources. In 2013, about 80% of Iceland's electricity was generated using hydroelectric power stations. Describe how electricity is generated in a hydroelectric power station. Include the useful energy transfers taking place. Note that word useful. We don't need to talk about any waste energy loss, so don't worry about adding that in. So, the first thing we've got in a hydroelectric power station is we've got falling water. If something's falling, that means it had GPE, gravitational potential energy, and that's being converted into KE. And we can use the shortened form okay. The water turns a turbine. So that's going to gain KE. Gains. And that in turn turns a generator. And the generator, what that does is it converts kinetic energy to electrical energy. So the generator turns KE to electrical energy. Okay, and that's all we need to say because we only need to include the useful energy transfers. Okay, let's compare wonderful Iceland with all of its renewable energy. The UK produces most of its electricity from fossil fuels. Many people in the UK leave their televisions on standby mode when not in use instead of switching them off. So that means that they're still going to be using electricity. They're not switched off. It is better for the environment if people switch off their televisions instead of leaving them in standby mode. Explain why. 3 marks. Okay, so in standby mode, electricity is used. This means more fossil fuels have to be burnt. You probably won't get a mark for this because it's given in the question, but it's worth it for making the argument coherent. Burning fossil fuels releases CO2. And why is that a problem? CO2 causes climate change. We've got a how science works question here. You can tell because they talk about scientists writing in newspapers or things being published in newspapers a lot in how science work questions. Scientists wrote in a newspaper, appliances that do not automatically switch off when they are not being used should be banned. Suggest why scientists alone cannot make the decision to ban these appliances. So what this is looking for is another factor that affects it. It's not just a scientific decision. What other factors take place? I'm going to say it's a political decision. But you could say there are social factors involved. You could say there are economic factors involved. Okay, figure 6 shows a fridge with a freezer compartment. Temperature of air inside the freezer compartment is -5, i.e. it's cold. The air inside the fridge forms a convection current when the fridge door is closed. Explain why. Okay, so where people have answered this in the past, they've got confused about when the fridge door is closed to think that means we're talking about the process of closing the fridge door and the effect that has. We're not. We're talking about it as a stable system without any air from the outside being able to get in. So, the freezer compartment is cooler than the rest of the fridge. So that cools the air at the top of the fridge. Okay, when air is cooled, the particles lose energy. And they move closer together. The cool air becomes denser. And because it's denser, because the particles are close together, it sinks to the bottom of the fridge. Okay, so there was warmer air at the bottom. That's now being pushed up because it's less dense. So I know what I've done here is I've given more than 4 marks, but I don't know exactly what the mark scheme's going to say. So I want to make sure that I've given as much detail as I possibly can. Okay, 6b, Table 1 shows information about 4 fridges. A householder concludes that the energy used in 1 year is directly proportional to the volume. Okay, so we're being tested on our understanding of this term directly proportional. Directly proportional means if one thing doubles, so does the other. Okay, explain why her conclusion is not correct. Use data from the table in your answer. So let's look for a doubling. We've got doubling of the volume here. And I can tell you just by looking at it that double 300 is not 630. So I can say when the volume doubles, the energy used does not double. And it says to use data in my answer. So, for example, fridge C has twice the volume of A, but 630 is more than double 300. Okay, new fridges are more efficient than fridges made 20 years ago. Give one advantage and one disadvantage of replacing an old fridge with a new fridge. Ignore the cost of buying a new fridge. Right, first thing I have to say, we can't give us an advantage that they're more efficient because they've told us that in the question. and you're being assessed on knowing some stuff rather than just being able to read words. A lot is being able to read words, and you'd lose marks if you can't read the paper, but you can't just repeat what they say on the paper. So what can I say as an advantage? If it's more efficient, that means less energy is wasted. That means I'm going to have lower electricity bills. Or lower running costs. Disadvantage, it's a pain in the butt having to get rid of an old fridge. So difficulties of disposal. Or it has to go into landfill. That would have been quite good. Talking about another environmental impact. Okay, moving on to question 7. We've got the apparatus drawn in figure 7 showing the data, how to collect the data needed to calculate the specific heat capacity of copper. The initial temperature of the copper block was measured, the power was switched on, energy transferred to the heater was measured using the joule meter, the temperature of the block was recorded every minute, temperature increase was calculated, and then we've got some results. Energy is transferred through the copper block. What is the name of the process by which the energy is transferred? Copper is a metal, so instantly we should be thinking conduction. Use figure 8 to determine how much energy was needed to increase the temperature of the copper block by 35 degrees. So we're going to 35 degrees. We're using a ruler if we have one. You should have one. Following the lines down. I'm exactly halfway there. That gives me 35,000 joules. Okay, so that's going to help me with the next part of the question. The copper block has a mass of 2 kilograms. Use my answer to this to calculate the value given by this experiment for the specific heat capacity of copper. Give the unit. Okay, so specific heat capacity, I get the equation from the equation sheet, but I need to rearrange it. And when I rearrange it, because the equation that they give me is energy equals mass times specific heat capacity times temperature difference. So we want to divide by mass and temperature difference so that we've got just specific heat capacity on its own over mass times temp diff. Okay, so we know that the energy change was 35,000 joules, the mass was 2 kilograms, and the temperature difference was 35 degrees. Okay, so we're effectively, see if I can do this without a calculator, the 35s cancel out, so that's 1,000 divided by 2, which is 500. So that bit's nice and easy, but we've also got to give the unit. Now I can't easily remember the unit for this one, but what I need to do in that case is I need to look at the equation. I know that the unit for energy is joules. Divide by means I put a slash in there. Mass in kilograms and temperature difference in degrees C. So that will give me a correct unit working through the equation. The experiment does not give the correct value for the specific heat capacity of copper. Explain why. So what I'm noticing here is there's nothing stopping the heat from leaving the copper block. I look back at my equation, at my experiment, and that's a problem. So energy is lost from the copper block. Okay, right, we've got some information about different light bulbs. The bulbs have the same brightness. Calculate the useful power output for the CFL. So we're looking at this one to begin with. So we've got efficiency and input power. Our equation sheet tells us that efficiency is equal to useful output divided by total input. We're trying to calculate the output, so output is equal to the efficiency times the input. So 0.42 times 14, and I'm going to need my calculator on this one. 0.42 times 14 equals 5.88. Then it asks me to calculate the waste energy produced each second. So a watt is just a joule per second. So we're already working in per seconds here. So our input was 14. We've got 5.88 useful. So 14 minus our answer from the previous question gives us 8.12 joules. Okay. A growth cabinet is used to investigate the effect of the light on the rate of growth of plants. As a picture, in case you can't imagine that. In the cabinet, the factors that affect the growth can be controlled. A cooler unit is used to keep the temperature down. It's programmed to operate when the temperature rises above 20 degrees. It's lit using 50 halogen bulbs. Changing from using halogen bulbs to LED bulbs will reduce the cost of running the growth cabinet. Explain why. And it's a 4 marker. So the first thing we need to consider is, so we're comparing LEDs with halogens. So that one with that one. We can see that the LEDs use less input power than the halogens. LEDs use less electricity than halogens. So we need to pay less for the light. But that's not 4 marks worth. And why have they talked all about this cooler unit that's being used when the temperature rises? Well, we've got to use our science brains here. If we go back to this information, the efficiency of a halogen is only 0.15%, whereas an LED is 0.85%, which tells us that the halogen is going to be giving off a lot more heat than the LED is. So, halogens waste more energy as heat. So if we're using LEDs, it's going to be less hot, so we're not going to have to run the cooler so much. So we save electricity on cooling. Okay. Scientists measured the rate of growth for plants for different intensities of light. What type of graph should be drawn? So different intensities, that's going to be a continuous variable. You could get any different value of the different intensity. If your independent variable is continuous, it's a line graph. Okay, intensity is a continuous variable. Nothing about it being easier to read or anything like that. It's whether it's a continuous or a categoric variable. Continuous gives us a line graph, categoric gives us a bar chart. Okay, we've got more information about halogen bulbs than LED bulbs. A householder needs to replace a broken halogen bulb. Compare the cost efficiency of buying and using halogen bulbs rather than LED bulbs over the time span of 48,000 hours of use. Your comparison must include calculations. It speaks for itself, that. if you've read the sentence, you know you've got to put some calculations in there. So the first thing I'm going to look at is the fact that the halogen bulbs have a shorter lifetime than the LED. So in 48,000 hours, you need one LED, or 48,000 divided by 2,000, which is 24 halogen bulbs. Okay, so the cost of one LED is £30. The cost of 24 halogens is £1.50 times 24, which is £36. So just looking at the cost to buy, we're going to be spending more if we use halogens than LEDs, but we also need to look at the operating cost. The operating cost of LEDs for 48,000 hours is £67.20. Okay, this is the operating cost over one bulb's lifetime. So again, we need to times it by 24. So for halogens, it is 16 times 24, which is £384. The total cost for LEDs is £97.20. For halogens, it is £420. So LEDs are, let's see if we can do a division here, divided by 97.2, more than 4 times as cost effective. Okay, so we've done lots of calculation in there, so that's answered that. We've probably given more information than we needed to get those 4 marks, but it's always worth, because you don't know exactly what's going to be on the marks game, giving as much information as you can if you've got the time available. Okay, that's the end of the paper. If you've got the time available, which you should do, you then need to go back and read through, particularly paying attention to your 6-mark question, where remember you are assessed using good English. So make sure you read that through to yourself, make sure the spellings are top notch, make sure it's got good punctuation and grammar, and most importantly, make sure it makes sense. And then you should be getting top A star grades. Thank you, goodbye.